Hello, everyone. Um, Today I'm going to talk about IEEE1588 end-to-end transparent clock. IEEE1588 standard version 2 was released 2008. Include ordinary clock, peer-to-peer transparent clock, end-to-end transparent clock, boundary clock, and measurement node. 2019 1588 standard version 2.1 was released. From clock type point of view, keep same, which are ordinary clock, peer-to-peer transparent clock, end-to-end transparent clock, boundary clock, and a measurement node. From standard 2019, here's how describe the clause 11, chapter 11 describe how transparent clock works. How make transparent clock work? There's two steps. Step 1, calculate offset from master on the slave clock. The offset from master equals time on the master clock minus time on the how to adjust slave clock. Two steps. First step, calculate offset from master clock to slave clock. Use following formula. The offset from master equals time on the slave clock minus time on the master clock. After calculate offset from master clock, go to step number 2. It adjust time on the slave clock to follow the time on the master. For example, the master side currently is 1 o'clock. The slave side receive time is 1 o'clock 01. Because this the message transfer from master to slave going through different devices, which means transparent clock in the middle, introduce some delays. So the offset from master is 1 second on the slave side. So after that, slave clock will adjust local clock based on calculation the offset, the value, which means 1 o'clock. So next time is 1 o'clock 2 seconds. After adjust clock, slave side time becomes to 1 o'clock 2 seconds. So this is how 1588 works on the slave side. So for the transparent clock, there are two different types. One is called end-to-end transparent clock. Another one is called peer-to-peer transparent clock. Today we are going to focus on the end-to-end transparent clock. For the transparent clock, start saying the most important things to calculate resident time, because the package start from master side going through transparent clock, finally reach to slave clock. The time delay will be introduced. When the package arrive ingress port on the transparent clock, will make timestamp. After going out the egress port from transparent clock will make another timestamp. Due to time delay, timestamp here, for example, is 1 clock 10 seconds. Here is 1 clock 15 seconds. Which means the latency introduced around 5 seconds. Another way, if the message sending from slave side reach ingress port on this side, make ingress timestamp. So after the message going out from transparent, make another timestamp called egress timestamp. So this is how to make timestamp on the transparent clock. So for the slave side, how to adjust local clock to follow master side. For the end-to-end transparent clock, there are different messages in order to calculate the offset from master. So there is a sync message, follow-up message, sending out from master side, going through transparent clock, received on the slave side. And the slave side send the delay request message going through transparent clock, arrive to master. And then master send the delay response going through transparent clock, reach the slave side. Based on this message, 15 message exchange between master and slave to calculate the offset from master on the slave side. So this is a message going through transparent clock. The introduced delay, the delay called residence time. So there is messages we mentioned before. The timestamp T1, master send out sync message. The T2 slave side received this message. If this transparent clock is a 2-step and the master is a 2-step, master will send a follow-up message. Two-step master, because this sync message cannot carry the residence time. The residence will be the T1 timestamp cannot be carried by sync message. The T1 timestamp will be carried by follow-up message. So when the slave side receives the follow-up message, to know, oh, the T1, what time T1 is now carried by the follow-up message. Next time, T3, slave side send the delay request. On the T4, master side received the message, and then master side send the delay response to the slave. So the slave side now T1, T2, T3, T4. These 4 timestamps. So total is called mean path delay from master to slave, calculated by this formula. It's T2 minus T1 plus T4 minus T3 divided by 2. So regarding end-to-end transparent clock, there are the 2 types. First one called one-step end-to-end transparent clock. Another one is called two-step end-to-end transparent clock. Now we can start from one-step peer-to-peer, one-step end-to-end transparent clock. So there is a master, there is a slave, in the middle is the transparent clock. For the one-step end-to-end transparent clock, the correction field of sync message equals resident time on transparent clock. For the any received follow-up message, do not make any change. So this is the sync message sending out from master side. On the egress port, make timestamp is called ingress timestamp. After going through transparent clock on the egress port, make another timestamp called egress timestamp. The sync message carry modified the correction field sent to slave side. So the time delay introduced by transparent clock is called resident time, will be carried on the sync message. If the master side, master is two-step master, follow-up message will be sent out from master side. However, the follow-up message going through transparent clock do not modify anything, just forward to the slave side. So from slave side, after received sync message and follow-up message from master going through transparent clock on the slave side will send out delay request message. After delay request message reach ingress port on transparent clock, we will make ingress timestamp. After the delay request message going out egress port on the transparent clock, will make another timestamp called egress timestamp. So the delay request message will be modified. So for the delay request message, correction field will be changed by adding resident time in the transparent clock. After received delay request message from slave side, master will send out delay response. delay response message just going through transparent clock, not modify anything, reach the slave side. So this modified delay request from slave side to master side modified only residence the correction field. Correction changed by adding residence time. Next one, I'm going to talk about two-step end-to-end transparent clock. For two-step end-to-end transparent clock, master side will send out sync message if the master is a one-step master. Transparent clock, before sending out sync message, just check the flag. If the flag, two-step flag is false, will directly send out the sync message without modification. When the sync message coming in the ingress port, make ingress timestamp, and then the transparent generate new follow-up message. The timestamp generated by sync message will put in the follow-up message. So for the two-step end-to-end transparent clock, the sync message not going to be modified. Only add correction field into the follow-up message. So the residence time actually calculated by the egress timestamp minus ingress timestamp, but these two timestamps generated by sync message, not by follow-up message, but carried by follow-up message. So another scenario is if the sync message, the two-step flag is true, which means the master side will send out a follow-up message. When this follow-up message reaches ingress port, make timestamp, the follow-up message will be modified after going out the transparent clock. The correction field of follow-up message will be added ready time, but this ready time actually generated by the calculation egress timestamp minus ingress timestamp of sync message, not a follow-up message. The sync message not do any modification. So after received sync as a follow-up from master side on slave side will send out delay request message. For the two-step end-to-end transparent clock, the delay request message not modified. However, this timestamp will be remembered on the transparent clock after master sends out delay response. TC received delay response and then send out delay response, but this delay response will be modified based on memorized the delay request message, egress timestamp minus ingress timestamp calculated. So this delay response method will be modified by the two-step adjustment transparent clock, and then send it to slave side. So there is a messages exchange between master and the slave. Sync message, follow-up message, and these two messages sent from master going through transparent clock, received on the slave side. After slave side receives these two messages, send out delay request going through transparent clock, received by the master side. Next step is master after receive the delay request, sending out delay response going through transparent clock, and then received on the slave side. So based on this messages exchange, the offset from master will be calculated. The final step on slave side is adjust time. After adjustment, the time on slave side, slave time will be following from master, which means slave side time will be synchronized with master side. We talk about the one step and two step end-to-end transparent clock, how they work from standard point of view. Next one, I'm going to show you the real example for the one step end-to-end transparent clock. So these are three devices. First one is Broadcom RSG2488 one-step grandmaster. And the middle one is Broadcom RST2220, the one-step end-to-end transparent clock. And the last one is Broadcom RMC8388 slave clock. So we configure the ordinary clock on the master, ordinary clock on the slave, and the transparent clock end-to-end transparent clock on the middle device. And transport protocol, we use layer 3 multicast on all these three devices. Yeah, for the delay, task delay mechanism, we configure end-to-end on all three devices. After device configured, we can check the clock status on all devices. The first device running as master, the second device running as end-to-end transparent clock, the third device running as slave. The current offset from master is -6 nanosecond, which means slave clock synchronized with master already. So we use the laptop connect to all three clocks and doing Wireshark capture. So the sync message sending out from master side, forwarded by middle transparent clock, received on slave side. So the we capture message on the ingress port of the endpoint transparent clock. See, we can see the correction field is that value, and we capture same sync message on the egress port, the showing different values. So the sync message forwarded by transparent clock and modified by transparent clock in the middle. So the resident time of sync message is this value minus this value is around 1.7 microsecond, which means the resident time on the transparent clock for sync message is 1.777 microsecond. So next one, we are going to check delay request message. Delay request message sent out from slave side, forwarded by one step into the transparent clock, and also modified. The delay response message sent out from master, forwarded by transparent clock in the middle, but not modified. So this is the message delay request modified by TC. We can check the delay request message. The egress port is 1.9 microsecond, and the ingress port is 0, which means the delay request message not forwarded and also modified by the one-step transparent clock. The delay response message is sent out from master side, forwarded by transparent clock, but not modified. So this resident time delay request the 1973 nanosecond on the one step transparent clock. So let's check delay response message. We know the delay request is modified by TC already. After master received delay request, send out delay response and forwarded by transparent clock. So we can check the ingress port. The correction field is 10549, but egress port is the same thing, 10549, which means this message not modified by transparent clock. So this correction field for the delay response message is 0, it's not modified. So if we configure the first device with the two-step grandmaster, keep not change on the second one and the third one. So let's see how it works. This pass delay mechanism configuration keeps in. So after configured, let's say slave side synchronized with the master side, and current offset -6 nanosecond on slave side. So we run wiretap on 3 clocks, try to capture message. So the master side send the sync message forwarded by transparent clock, and so we check the ingress port on this transparent clock is 0, and the correct field of the sync message on the egress port is 1789 nanosecond, which means sync message is modified. So the residence time for sync message modified is 1789 nanosecond. So next one, we check follow-up message. Follow-up message sent out from master side, forwarded by the transparent clock in the middle. We do the same thing, capture message on the ingress port and the egress port, compare correction field. So the correction field on both messages are 0. So the follow-up message is not modified. So think only modify sync message, follow-up message not modified. So next one, I'm going to show the two-step example for two-step end-to-end transparent clock. So we still use 3 devices. The first one is the Rubicon RST2488 two-step grandmaster. The middle one is the Rubicon RSG2288 two-step end transparent clock. Slave clock is ARM is RMC8388A. We have 3 laptops connected to 3 clocks and doing Wireshark capture. So this is the configuration, end-to-end transparent clock and ordinary clock combination, which means hybrid clock configured in the middle. All the transport protocol using layer 3 multicast. The ordinary clock, transparent clock. So for the pass-delay mechanism, we configure end-to-end on all 3 devices. So after device configured, we can find first device running as master, second device running as slave and transparent clock combination. The slave clock running as slave is current offset minus 19 nanosecond, which means synchronized with the master clock. So the master side sends sync message forwarded by two-step transparent clock, and then we can check sync message on the ingress port. The correction field is 0, and the correction field of sync message on the egress port is 0 as well, which means sync message is not modified by two-step transparent clock. So this correction field of sync message not modified. See? So next one is we are going to check follow-up message. Follow-up message we capture on the ingress port and check correction field is 0, and forwarded by transparent clock, the correction field modified to this value. So the follow-up message modified by transparent clock introduce the resident time is this value. So the next one, we are going to check delay request message for the two-step end-to-end transparent clock. Delay request message sent out from slave side, forwarded by transparent clock. And after received delay request message on the master side will send it out delay response message, then forwarded by transparent clock and modified by transparent clock. So this delay request message send it out from slave side. We capture message on the ingress port of the transparent clock. See the correction field is 0, and we check same message on the egress port. The correction field is 0 as well, which means the delay request message not modified by two-step transparent clock. After receive delay request message from on the master side, the master will send it out delay response message. And forwarded by transparent clock. So the forwarded and modified, but this one showing it request say is same is not modified. So delete request message is not modified. So next one we check the delete response message. The response message we capture on the ingress port is 0, but the egress port is 5116066 nanosecond, which means the delete request message, delete response message modified by two-step transparent clock. So this delete response modified, we introduce the resist time is 5116066 nanosecond. So today we shared the information about a one-step end-to-end transparent clock, two-step end-to-end transparent clock, and also two examples. One is for one-step transparent clock, another one is for the about two-step transparent clock. Okay, this is everything today. Thank you for watching. Bye bye. See you next time.